The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so one of the things that is mysterious about spectroscopy is how do you assign spectra? And so I've always felt that it was a useful thing to illustrate how you assign what would normally be considered the easiest kind of spectrum, an atomic spectrum. It actually turns out to be a little harder to assign an atomic spectrum than a molecular spectrum because the critical information appears only once or twice in an atomic spectrum. And so it is the perfect Sudoku problem where you have to put together all of the critical clues in the right way. There's only one way to do it, and it seems very tenuous, but once you've gotten to the end, you know it was right. It's rock solid. And so what I'm going to try to do is to give a little bit of a sense of how this is done. And in order to do that, I'm going to ask you questions and use an example which isn't in the notes. So, iron. The ground state of iron has a configuration 4s squared 3d6. And so this is plenty complicated, and so I'm going to try to draw on examples from the spectrum of iron. But before we get there, suppose you had an atomic spectrum. What would you look for? How would you begin to figure out what you've got? I mean, when you have a spectrum, often you don't even know what species it is. Because frequently, when you record a spectrum in emission, you're doing something very violent to the system. You're running a discharge, or an arc, or you're doing something terrible. And so you could very well be looking at a spectrum of an impurity. Maybe intentionally. And almost anything you stick into a discharge is going to have sodium in it, it's going to have carbon in it, it's going to have oxygen in it. And so there's going to be a lot of things that you didn't expect if you were looking for a spectrum of chromium or something like that. Okay, so you don't know what the species is, let alone what its charge state is. And so how do you begin? What would you do? I mean, there's no wrong answer. Yes?
I mean, I would look for kind of the lowest energy transition. Actually, I don't know what's the highest energy transition.
Okay, so you can do both. But so lowest energy, you mean you would work in absorption, or lowest energy you would just look for long wavelength emission?
Yeah, well, I mean, I'm a theorist. I sort of went lowest end, but I realized you can't really tell that from the spectrum.
Yeah, that's true. I mean, when if you have a discharge, it's a highly non-equilibrium system, and you don't know. Just you can perhaps make it gentle so you don't have ions, but you can't make it gentle so you only have low-lying states. Now, if you're working in absorption, you can keep the temperature relatively low. But if you have something, if you want to do an absorption spectrum of iron, it's going to be pretty bloody hot just to get some iron into the gas phase. And so you don't know that everything that you're observing is a transition from the ground state. But you do want to make some hypotheses about what are the relatively low-lying electronic configurations and the states from those low configurations. Because the low-lying states are almost certainly going to be involved. The transitions will terminate in them, or they will originate from them, but the low-lying states will play a disproportionate role. So that's good, low-lying configurations. You also said highly excited, and I think you were probably nibbling around the concept of Rydberg states, or not. I don't want to put words into your mouth, but if you say yes, then I'll be happy, because I'll then riff on that for a minute.
Okay, I won't lie, that's not actually what I was going for.
You won't?
I said I won't lie, that's not what I was looking for, actually. I was saying, you know, the high energy transitions might tell you where some of the low-lying states are.
Well, that's true, because the higher the energy, the harder it is to fit between the ionization energy and the ground state. However, what's the typical ionization energy for an atom?
20 electrons.
That's high. That's too high. That's inert gases. Yeah, yeah. I mean, you know that as a theorist, that's reasonable. But the number. I mean, yes, could be. You know, it's not hydrogen, and helium. You know a lot about, and because that's how you learn about two electron systems, and so you know what helium is, and it just happens that helium is really high, and so 10 electron volts is sort of on the high edge. Well, that's pretty typical, and 5 electron volts is sort of about, it's almost as low as it gets. So if you're looking for a high frequency transition because that's all that will fit, you're going to be in the vacuum ultraviolet. And so that doesn't get transmitted through air, so you need special apparatus. So it's a good try. And it might be better for molecules, because molecules have a lower ceiling. They dissociate at lower energy, like 6 or 7 electron volts, and so there's going to be a limit on how high energy you can have, and that might just work, but I don't think it'll be very helpful. Rydberg states or Rydberg series are extremely useful, because almost everything has Rydberg series, and Rydberg series have the nice characteristic of converging. Whoops, too fast. But the levels get closer and closer together, and you have an infinite number of them before you get to the limit. And so that's a fantastic thing, because it tells you which way is up. And so if you see series of transitions which look like they're converging according to a Rydberg-like equation, you know how to arrange your level diagram as which is the upper state and which is the lower state, which turns out to be one of the hardest things. Because there's nothing about a spectrum that tells you assignments, nor about what is on top and what is on the bottom. Because when you figure out a group of upper levels and lower levels, there's no reason why the whole thing couldn't be turned upside down. But Rydberg states are unique in the sense that they tell you which way is up. There's another thing that tells you which way is down. If you can figure out something about the lowest lying state, what will be its symmetry or what will be its properties, then if you happen to see transitions involving that state, you know which way is down. But if you don't see that, then you still have to worry about this. So this is really an it's a puzzle. I don't think it's a terribly important puzzle, but it's a beautiful puzzle, and you have to solve it in order to get to the important problems. And so some people just love assigning spectra because it's a wonderful challenge, but the challenge should have a purpose, which is to, yes?
Can you also use the most intense lines as a beginning point?
Yes.
Like with sodium, you see these huge B lines, you can sort of already know what they are before you even do anything.
Okay, intense lines, every atom has a few really intense lines, both in absorption and emission. in absorption, of course, the most intense lines will be transitions out of the ground state to some favored low-lying excited state. In emission, there will be, you deposit energy into the system, and it cascades down, and eventually it gets to a low-lying excited state, or a bunch of low-lying excited states, and they all, they generally, many states, and it sort of funnels to a few, and then there's one transition that takes you back to the ground state. And so that there is often a small number of really intense lines, whether it's absorption or emission, that can be anticipated in advance or have been figured out. So there's a book called the MIT wavelength tables. And in here, there are, in wavelength order, a huge number of atomic lines for neutral atoms and ions and so on. And it's a finding list. So the important thing, though, that this table tells you is that your measurements had better be really precise. Otherwise, you're wasting a lot of time. Because if there are tables which are 7-digit numbers, and there's lots and lots of atoms and lots of transitions, if you didn't make your measurements accurately, this table is useless to you. And so even if you don't know what you are looking for, it's a good idea to make accurate measurements. Accurate, absolute measurements. Well, that's what accurate means as opposed to precise. Okay. And there are also these wonderful tables of energy levels. Once you have a spectrum, then you convert it to energy levels. And so you can, if you think it's, what atom it is, you can look up the energy levels. And Sam's comment about sensitive lines, there are these things called Grotrian diagrams. And basically what they do is they show you the patterns of levels, and it indicates how population would flow down through bottlenecks, and there would be a few sensitive lines. These are enormous things. And
what book is that in? Is that also MIT?
No. This is published by Elsevier. So that means this book must cost $200 or $300 because it's published by robbers. Okay.
Is it easy to predict accurately which way the energy will flow and what transitions are going to be the most?
Yeah, if you know what the energy level diagram, you can. It's often possible to say, okay, as you come down, there's a relatively small number of paths, and so that all of the population gets funneled into a relatively small number of transitions. That's a fairly unreliable way of making progress. Okay, so one thing that is never a good idea when you have a spectrum, molecule or atom, is to attempt to predict it, to model it by some sort of computer model. Because the models are never going to provide uniqueness. And the way in which you make assignments is by discovering coincidences, energy level differences that are repeated multiple times. Those are called combination differences. And these combination differences are much more abundant in molecular spectra than in atomic spectra. So, what I'm going to do is I'm going to try to show you the importance of combination differences, how you find them, what you learn from them, and that sort of prepares you for dealing with molecular spectra. Okay, so let's begin. We think we're going to have a spectrum of neutral iron. What would we do? Well, we would immediately try to figure out what would be the low-lying electronic configurations of iron. And I wrote this configuration, which if you had been recently in freshman chemistry, you would also have written this as the ground state configuration.
But isn't it actually 3d6 force too?
What?
Aren't the d's lower than that?
Yes. There are various conventions about the order in which you write these things. And Sam is right that the normal convention is you write the most stable orbitals first and the least stable last. It's not always written that way. Okay, so, but that's an important clue. So what do we expect about the low-lying configurations of iron? Well, we have, I guess I'll write it the right way then, 3d6 4s squared. What are some others that we might expect?
3d7 4s.
What else?
3d8.
I wouldn't go for that.
3d5. 4s2.
Why did I do this? We have a parity selection rule. Parity is -1 to the sum of the little l sub i's. And transitions always are between states of opposite parity. So basically what you want to do is write the two lowest configurations of one parity and the two lowest configurations of another parity. And that pretty much ensures that you've got everything that you need, more than you need. Okay, and these two configurations are even parity configurations because you've got nothing but even L's, and so there's no way the sum of the L's is going to be odd. Now you could make a state that has an odd total L, but the parity for atoms is the sum of the little l sub i's. Okay, so one way to have odd parity is to have a p electron. And so we could imagine having 3d5 for s for p as well.
Force 2.
Yes. Right. D5 is always specially stable, so that's good. And so we have an S to P or a D to P promotion. These, it's hard to guess which one of these is going to be lower. I'd put my money on this one. But I don't know for sure. Okay, so we have 4 configurations. Now, let's look at this one. And now there's the method of boxes. You could figure out what is the lowest, what are all the states from this configuration, and which is the lowest of them. But there's a shortcut. If you just want the lowest, you know that you have to put the electrons into different orbitals. And so we have 2, 1, 0, -1, all with the same spin. And so this will make a quintet delta state, a quintet D state. 2 plus 1 minus 1 is 2. So that's the maximum M sub L. 1/2 plus a half plus a half plus a half is 2. That means S is 2, and that's quintet. So we have a quintet D state that's going to be the ground state of that configuration. Why did I say it's a ground state? Because it's got the largest possible spin. And it's also constructed to have the largest possible spin and the largest possible L. So it's really, you don't have to do boxes in order to figure out the ground state. And it's D6, and so you know immediately that this is an inverted D state from Hund's rules. I've told you the Hund's rules, but most of you don't remember them. And none of you know, well, most of you probably don't know where they come from. And I have promised myself I won't show you, but I hope you'll be curious about it. Okay, so if you have a more than half-filled shell, the spin orbit splitting has the opposite sign from usual. And so instead of having the minimum possible J at the bottom, you have the maximum possible J at the bottom. And the maximum possible J is S plus L, so 4. So we have a quintet D4 ground state of iron. I believe that is the ground state. I'd be very surprised if it weren't. And so we begin by looking at, expecting that there are going to be transitions involving the ground state. And so it's a quintet state. So we expect that there will be 5 components. And so we have quintet D4, 3, 2, 1, and 0. Okay, so there'll be spin orbit splittings here. Here we go over there. So spin orbit is enormously important for making sense of atomic spectra. It's not the most important thing, but it turns out to be the key for arranging things in groupings that you can assign. And so we have to look at the spin orbit Hamiltonian briefly. And there are 2 ways in which we write the spin orbit Hamiltonian. One way, well, there's lots of ways. There's 2 ways I write it. And there's 2 ways most atomic spectroscopists write it. And this does not correspond to the way theorists would write it. But we have some radial integral, and we're summing over electrons. And that's the form of the spin orbit operator that I like. And this operates on determinantal wave functions. And if I had taught you how to evaluate matrix elements of determinantal wave functions, you would be able to immediately look at this. The nice thing about this operator is it's a 1-electron operator. It's a product of 3 terms all operating on the same electron. These are wonderful. It doesn't require any skill, and so that's good for determinantal wave functions. But there is another way of writing it, and that's zeta of Ls. In other words, some constant which is appropriate for the particular Ls state times L dot S. Now, these 2 look similar, but this operator is of especially important form because with this operator, you can have matrix elements between states of different S. But for this operator, you can't. So this is a replacement of the true operator. This is also a replacement of the true operator, but it has all of the sophistication you need for dealing with almost every problem. This one is convenient and is useful for dealing with the energy levels of multiplet states at this stage. So we're going to be using this.
Is this correction includes all relativistic effects or not?
These are both, spin orbit is a relativistic effect. These 2 operators both deal with the relativistic effects in exactly the same way. It's just this one has been stripped of almost everything.
So what if the last one, L, is equal 0?
Then there's no spin orbit splitting.
But how then you account for changing of the mass of the electron? Because that would be...
So relativistic, this is not all of the relativistic effects. It's just that spin orbit is a relativistic. There's other things that have to do with the relative energies of states, but this, so, okay. All right, so we have this. This is a constant for a particular multiplet state. And the way in which you assign an atomic spectrum is you look for groupings of transitions which seem to be related. In other words, relatively many transitions over a relatively small interval separated from the next group of transitions. Those are multiplets. And these are transitions between multiplet states, and that's how you begin to make an analysis. And spin orbit is key because it determines the spacings of multiplets. Okay, so we'd like to know how to evaluate matrix elements of L dot S in the basis set L, S, J, MJ. We'd like to know. So this is the eigenvalue of L squared, or it's the quantum number that tells you the eigenvalue of L squared, S squared, J squared, and JZ. Okay, so it would be nice if we could put this thing in a form where we just know immediately how to write down what it does to a zero-order function. And so we know that J is equal to L plus S, J squared is equal to L squared plus S squared plus 2L dot S. Ha, there it is. L dot S just appeared here, and J squared, L squared, and S squared, J, L, and S, they're here. So we know how to use this form to get the matrix elements of this. So L dot S is just 1/2 J squared minus L squared minus S squared. So it's going to be JJ plus 1 minus LL plus 1 minus SS plus 1. And so immediately we can know what the expectation value of the spin orbit operator will be for each term in an LS multiplet. And please ask questions. This one I expect you to understand. Okay, so I don't, all right. I mean, there are things I don't want to talk about, but this I really want you to know. Okay, so we'd like to calculate the first order perturbation corrections, which are diagonal matrix elements of the perturbation operator, for the various terms in a spin orbit multiplet. So what do? Well, we know that the energies are going to be 1/2 times this zeta times JJ plus 1 minus LL plus 1 minus SS plus 1. The reason these are the operators, these are the eigenvalues, or not the eigenvalues, what does the operator do to the function? Okay, so we're going to have this. And it's even simpler. We'd like to know, say we have a quintet D state. We'd like to know the energy difference between quintet D4 and quintet D3. Well, we don't even care what L and S are. They don't change. So if I want to know the energy difference between quintet D4 and quintet D3, I just write 1/2 zeta times 4 times 5, 20, minus 3 times 4, 12. And that's 8 over 2, 4 zeta. 4 zeta. 4 is J for the higher J state. Okay, and what you're going to find, you could do this for yourself. What you will find is, if you're looking at the 4-3 interval, you'll get 4 zeta. If you're looking at the 3-2 interval, you'll get 3 zeta. If you're looking at the 2-1 interval, you'll get 2 zeta. And the 1-0 interval, you'll get, if there is a 1-0 interval, yeah, it is, you'll get zeta. Okay, so we have the expectation that the spacings between spin orbit components are going to have certain ratios. 4-3, 3-2, 2-1. They're going to be, if you have integer j, they're going to be integer ratios. If you have half integer j's, you'll have half-integer ratios. And that can even tell you whether you've got the ion or the neutral. So this is telling you what to expect. That there's going to be level splittings which are going to have nice simple relationships to each other. Okay, so now suppose we're going to look at a quintet F to quintet D multiple. Yes.
I thought you said last time that in certain of Hund's cases, that spin orbit would be diagonal, and certain it wouldn't. So would this always work, or would it depend on?
Won't work. There are quintets, triplets, and singlets. And there are off-diagonal matrix elements between the same states with the same value of J, but different L and S. And so the level patterns will be distorted by off-diagonal elements.
But in a multiplet, this will work.
No, I mean, suppose you had this quintet D, and suppose there was a triplet D somewhere not too far away. Well, then 3 of these will get pushed down. So the intervals will be distorted. So, you know, there is this magic decoder, but it's imperfect. You have to be able to look for near integer ratios, and you have to be willing to accept small deviations, and then you have to explain why you had these small deviations at the end. So it's not as trivial as it might seem. You know, it's sort of second order Sudoku. But it's, you know, all right. So we have some predictions here, and now what I want to do is illustrate. Well, okay, I didn't say anything about selection rules. Selection rules for transitions. The transition moment is a 1-electron operator. That means only one spin orbital can change. And or if you're looking at configurations, you can only change one of the L's by 1. The photon is like an angular momentum L of 1, which adds to the L's of the individual. But you can only change. So we have odd parity, or the transitions change parity. Delta L equals plus or minus 1. Delta big S is equal to 0. Delta big L is 0 plus or minus 1. Delta J is 0 plus or minus 1. But 0 to 0 is forbidden, despite what is incorrectly stated in the notes. If you will notice diagrams, you'll discover I not only said that there are some 0 to 0 transitions, but among the transitions they are among the strongest, which is absolutely wrong. It's just amazing what I will write for many, many years without catching it. But you know, you get older, you get smarter in some ways and dumber in others. So this is not okay. So using these rules, you can then make some predictions about what will happen in transitions between 2 multiplets. And so quintet F to quintet D. We're going to do 2 examples because I want to show an important fact. So quintet F, now let's just say quintet F is inverted just like the quintet D. So quintet F will have a lowest possible value of J of it's L minus S.
1.
Right. So, so we have a level diagram downstairs, which has 5 levels, and a level diagram upstairs that has 5 levels. And so let's label them 0, 1, 2, 3, 4. 1, 2, 3, 4, 5. Now the zeta for F is going to be different from the zeta for D. And if you had all gone to the one electron form and evaluated the matrix elements in that basis, you'd find how the many electron zetas, the zetas for an LS state, are related to the one electron zetas which exhibit periodicity and are all tabulated in my book. So you could know the zeta for the quintet F and the quintet D, but you don't need to. Okay, so there are these states. I brought an extra color of chalk because I wanted to illustrate something. Okay, L is one higher than, L in the upper state is one higher than in the lower state. So there are going to be a series of strong transitions where J changes in the same direction as L. So there are going to be 5 relatively strong transitions.
How do you know those are relatively strong?
Because delta J has the same sign as delta L. The electron operates on the spatial coordinates. And so it doesn't do anything to the spin. The spin is a vector that's left.
Oh, okay, so it's by the sort of Wigner rule that they'll be really allowed.
Yes.
Okay.
Now, you can also have delta J of 0 and delta J of -1, or the other sign. And so let me draw in the other possible transitions. Well, 5 can only go to 4. It can't go to 3. So that's an orphan. But 4 can go to 4 as well as 3. So let's draw next to that. Oh, that doesn't help very much. Can you see that one's yellow and one's white?
Not really.
I like the white chalk. Okay, so I'll stick with that. So there's one transition from here. There's 2 from here. There's going to be 3 from here. 3 to 4 and 3 to 3, which we've already got. No, we haven't. And so this is the strong one. This one is weak. This is very weak. And similarly, we can draw them as there'll be 3 from here. And let's see how many from here. 2 from here. So I better draw them all in. So we have that guy. That's 2 to 3. Whoops. And 2 to 2. Okay. So we have 1. We have 1 here, 2 here, 3 here, 3 here, and there's going to be we go 1 to 0, 1 to 1, and 1 to 2. So there's going to be a total of 9 components. Okay, and the important thing is that you'll notice that these 2 transitions sample this interval. These 2 transitions sample this interval. So you see that certain intervals are appearing twice. So you have 2 transitions. You see, okay, here, these 2 come from the same level, and you get that interval. Okay, you have this and this from the j equals 3 level. They also sample that interval. No more. The same interval appears twice, sometimes. Once for others. But when they appear twice, you're off to the races. Whenever so what you do is you observe all the lines and you take all the possible differences. So we have 9 transitions in this multiplet.
Why are there 9? I'm sorry.
There's 1, 2, 3, 3, 3. Oh, 12. I outsmarted myself. So there's 12 numbers, 12 8-digit numbers, and you take all the possible differences among the 12 8-digit numbers. How many is that? How many are there?
12 choose 2.
It's probably right. A lot of them. And you look at them, and you look for repetitions. And those are telling you something. So the ones that are repeated, you know those correspond to certain spin orbit intervals. And what you want to do is find magic quartets of lines. So we have an interval here, let's call that A, and that same interval here. And so you see the interval appearing twice, and you see the same interval appearing twice this way. So this tells you how to arrange 4 levels, 4 transitions. And so you have a repeated difference that will be in one state, and a repeated difference which will turn out to be in the other state. You don't know which. Okay? But as soon as you've calculated all these differences, then you can pick out pairs of transitions that exhibit the same difference. And then you can find ways of grouping them in this magic quartet. And then what you find is that you can link that with another grouping, and you get C, C, D, D. And so this is how you would begin. You know, as soon as you find repeated intervals, you start arranging things. And what you do is you always arrange the numbers in columns and rows so that they're monotonically going in the same direction. Okay. And now you have A and D. And you're going to look for the ratio of those, and that's going to tell you J. Because the ratio, you know, you have, you can go from J equals 5 to 0. And so you have a 5 to 4, you have a 4 to 3, you have a 3 to 2, a 2 to 1, and a 1 to 0. Of course, that one doesn't help you. So you're expecting ratios of intervals that are 5/4, 4/3, 3/2, 1/2, 2. If you see something close to that, you know immediately what's starting to go on. You know, if you see 5/4, you know there's one level that has J of 5, one level that has J of 4. And then if you see a linked, if you see 4/3, so if you see a transition that is a part of a 5 to 4 and a 4 to 3, then you've started to build this. Okay, so this is what you do. It looks complicated, and you know, but it is amazing how you build up these patterns. Now, there are more things that happen. You collect all of the possible repeated intervals, and from the number of repeated intervals and from some of the ratios, you start to know what J maximum is and what J minimum is. And another fact, if delta L is 0, in other words, if you have states of the same L, you get the maximum number of repeated intervals. I can't possibly lecture to you about how to do this without you actually working a problem. And, but you know, this is how it begins. You just take this table of numbers and you calculate all the differences. Then you take ratios of the differences, of the repeated differences, and you make conclusions about what does that say about J. And then you make conclusions about the range of J from the, you know, these intervals. This is the smallest, this is the biggest, and how many of them, and you start to know what the multiplicity is, what the maximum J is, and you discover that if L doesn't change, you have more repeated intervals than if L does change. And so very quickly, you're able to build up a level diagram. And you know, the only way I could really teach you to do this is now to put a bunch of numbers on the board and assemble this level diagram. And what I recommend is that you look at the page, where is it? Page 5 of the notes. And we have here this multiplet table for iron. And you notice there's 5 spin components and 5. And so we have the energy levels, the transition frequencies. And the highest is on the top and the lowest is on the bottom. And there's 3 magic quartets. And the energies are also increasing this way, decreasing that way, and we have, and so you can see that there's a interval of 104.5 and 215.5, so that's a 2-to-1 ratio, and then we have 215, 294. Well, that's or 290. That's 1.5, and so I told you we have 2-to-1, 3/2. So you'll see immediately from these intervals that, you know, they're being approximately repeated here. There'll be defects because of spin orbit distortions, but you immediately can determine what is J maximum. You know, because there are 5, it's a quintet state, and so you can determine what L is for both states from this kind of a table, and it's done. Except you don't know up from down, because this table could just as well, you know, you don't know whether this state is on the top or turned upside down on the bottom. If it's the ground state, you know that the ground state is going to be, well, I drew it the wrong way around. The ground state should have had the maximum J on the bottom. So if you know that you have the ground state, you know that maximum J is going to be on the bottom for iron. And so you don't have the up-down ambiguity. You need to know something to decide whether your level diagram is like this. Oh, shit, how do I do this? I got to turn that over, and I got to turn that one over. Okay. Or like that. So, yes. Okay, I got it. And one way is to know the possible signs of the spin-orbit coupling constants. One way is to know the possible values of the spin-orbit coupling constants. One way is somehow to have one of these things linked to Rydberg series, and then you know up from down. So there's a lot of ways, but this is how you begin. You have to begin by grouping 4 transitions together in a quartet, and then matching the corners, and you just start to build. And that's always the way it works in spectroscopy. You figure out something that you can identify absolutely, and then you spread your domain, building on what you know. And the subtle thing is, this is an imperfect pattern finder. there are distortions in the patterns. Usually the distortions don't stop you, but sometimes the distortions are so serious that you have to model that says, okay, well, I think it's this, but I have a spin-orbit interaction that messes up the pattern. I have to represent that. You can do that. Okay. Yes?
What would it take to estimate the spin-orbit constant from theory? Would that require...
Well, some theorists won't do it, and some will. I mean, it's not a standard quantity. And so if people are using their inherited codes, and the codes don't have spin orbit, then they'll say, don't know. However, you know how the spin orbit constants are going to vary. That, you know, spin orbit scales as n to the minus 3, L to the minus 3 approximately. And so, and Z to the 4, Z effective to the 4. So there are things that you can do to make predictions of what you would expect for a particular atom. And there are these big things that happen when you go from D4 to D6 because the sign of everything switches. So, but all of the important spin orbit coupling constants for atoms are tabulated in my book. Okay.
Can I ask one other question right now?
Absolutely.
Okay. Real spectra of iron.
Yes.
There are multiple isotopes of iron that might have small differences, and if one has 7-digit numbers, you can probably see those differences. Can you use the fact that there are multiple isotopes to help you, or is it just a pain?
Well, actually, the isotope shifts for atoms are really small, but what you can do is there are isotopes that have large hyperfine structure and small hyperfine structure. So what is more likely to happen is you have a level which has no hyperfine because it's even, even number of neutrons, even number of protons, or and one which is even odd. Or sometimes you have nuclei where the spin, the nuclear spin coupling constant, I forget the name of it, the nuclear magneton, or what? No, it's not. I don't remember what it's called. But some of them are bigger than others, and so. But what you frequently see is not isotope shifts, but you have sharp lines and broader lines, or split lines, and that will often tell you which species it is. But you cannot count on there being resolvable isotope shifts. You can have broadenings. You really need very high precision, and that means that you have to also understand the electronic structure very well, because you could get small shifts from other things. All right, so
part of that, let me follow one quick follow-up, that when a lot of this work was first done, maybe you couldn't resolve those lines at all.
Well, actually, the hyperfine in mercury is pretty big, and so there, some of the. It's very common when you have multiple isotopes that you can tell that there's something going on, because there will be one that has nuclear spin, and maybe it's not very abundant, but you can generally catch it, and that usually tells you which one it is. Okay, there's two other methods for figuring out assignments. Now, I know that I'm just about out of time. There's the Zeeman effect, and there's the Stark effect. After all, you have J's, and J's split into two j plus 1 values of mj. So if you could split the m components, then you could determine j assignment simply by counting. And that would be really neat. And the trouble is that you need really, really big magnetic fields and even larger electric fields. And the Stark effect is actually a complicating factor for, okay, the Zeeman effect, you'll simply split all the m levels. But one of the bad things that happens, you split the m levels upstairs and downstairs, and often by the same amounts. And so you end up getting a spectrum which is more complicated, and you can't count. It's just more complicated, and there are many blended features. But you get 1.4 megahertz per Gauss times the times lambda, I'm sorry, m sub L plus 2 m sub S. So you can figure out what the Zeeman splittings would be, and sometimes the G values are more complicated than this, but I'm just.
Where does the 1.4 megahertz per Gauss come from?
That's just the conversion factor of the Zeeman the electron, the Bohr magneton, which is equally useful for electron or orbital angular momentum or spin, and the Zeeman effect. So that's a fundamental constant that actually physicists sometimes try to measure really accurately. And so then there's the issue of how do the various angular momenta couple to the external magnetic field, and in some coupling limits it's sort of like that. Now the Stark effect is like the electric dipole transition. It's odd parity. So the Zeeman is is a splitting of a particular state without necessarily off-diagonal matrix elements. There are off-diagonal in L matrix elements of the Zeeman Hamiltonian, but if the states are far apart and the Zeeman splitting is only a few wave numbers, that's almost always ignorable. But the Stark effect is always off-diagonal in spin orbit components. In fact, it's always off-diagonal in electronic states because you have to change little l, so you have to go between an even configuration and an odd configuration. And so the Stark effect is a really, really bad way to make a living, and it doesn't lift the degeneracy of positive m sub j and negative m sub j. And so if you could resolve things, you would not resolve 2j plus 1 things, you'd resolve j plus 1 things. But the splittings are much smaller. But if you're doing very high resolution spectroscopy, as we do, by doing millimeter wave spectroscopy, yeah, sure, you can resolve the m's and count. Okay, so I hope that this was instructive, that you basically build on what you know, and you use simple empirical ratios of things, and you start to build more and more pieces that are linked together in a way that you can understand. And so the best way to do this is to take, say, the numbers from this table on page 5, strip them out of the table, stick them into a computer, and calculate all the differences, and then try to reconstruct the table without looking at it. And there's only one way. You will find that, that there will be defects in the sense that the ratios aren't going to be exactly what you predict, but it would be, I recommend it. And so we're going to start on molecules tomorrow morning. I'm going to talk about the born-oppenheimer approximation and the diabatic and adiabatic representations, starting to get into good stuff. So that's it. Thank you.
Does anyone still work on atomic spectra in the classical sense? fundamental problems with
Maybe a little bit. I think that what you would find is that if there were funding to do it, people would do it. Whether we can agree that it's worth doing, that's a serious subject of debate. There are regions of the level diagram that haven't been mapped because you have to have several excitations from the ground state, and so there are many open shells, there's high multiplicity, there's complicated stuff that could occur. Do you learn something by dealing with that? Well, I don't know. But there isn't a lot of activity in assigning atomic spectra. And instead, people use what you know about atomic spectra in order to get at more complicated, more important, fundamental things.